So we continue our quest for this grand equivalence theorem for compact metric spaces. Um, and now we're going to get to another concept, which is important regardless of whether we're talking about compact or non-compact things. And this is a more geometrical concept, and it's related to the idea of a space being totally bounded, right? Remember, I introduced this terminology of totally bounded in that grand equivalence theorem, but I didn't explain what it was. So bear with me for a second, because before we define that, we need some other concepts. Okay, suppose I have a metric space X and a subset K, right? So the subset could be the whole space, but doesn't really matter right now. I want to define two things related to this set. So an epsilon net for K, epsilon is just some constant greater than 0. So an epsilon net is a set R that approximates K within error epsilon, meaning that for any element of K, there is an element of R at distance epsilon from the element of K. An equivalent way of saying this is that K is covered by the closed balls of radius epsilon centered at the points of R. Right? So the way you should think of it is that R is a discretization of K, and in the sense that, right, so we're going to be especially interested in finite R, and whether a certain X has a finite epsilon net or not. In that case, we have a finite discretization of K, which has an error or tolerance epsilon. That's one concept. Another concept is the concept of an epsilon packing. An epsilon packing is just a collection of subsets of points in, K, such that any two distinct points in there are a distance greater than epsilon from one another. So here, you're trying to cover everything with balls of radius epsilon, right? So here, doing something different. You're fitting points into K in a way that keeps distances between points at least epsilon. And now I'm going to define two geometric quantities associated with the metric space. So epsilon covering number of K like that is the size of the smallest epsilon net for K. This could be infinite, right? So there's always an infinite epsilon net. For instance, I can take R to be the whole set K. And here talking about the minimum, this is going to be either a natural number or infinity. Okay. And this is the epsilon covering, and there's the epsilon packing number. Which is pk epsilon. That's the maximum size or the sup of Q. Q is an epsilon packing in K. So again, this could be infinite, right? It could be that I have either an infinite epsilon packing in K, or that I have larger or larger packings of sizes 1, 2, 3, so on and so forth up to infinity. Okay, what is a totally bounded set? Well, by definition, that means that for all positive epsilon, and K epsilon is finite, meaning for all open epsilon, I can find a finite epsilon net, or for all open epsilon, there's a finite collection of closed balls of radius epsilon that cover the entire space K, that cover the entire set K. It turns out that I define totally bounded in terms of covering numbers. There's an equivalent definition in terms of packing numbers, which is actually a consequence of a proposition that I'm going to state now, which is that for all positive epsilon, no matter if these numbers are finite or infinite, the epsilon covering number is bounded by the epsilon packing number, which is bounded by the epsilon over 2 covering number. Therefore, it's equivalent to ask that nk epsilon is finite for all epsilon, or that pk epsilon is finite for all epsilon. So I can define a totally bounded metric space, a totally bounded subset of a metric space as a set whose epsilon packing numbers are finite for all epsilon. Okay. How do we prove this? So there are two inequalities here, right? So I'm going to start with this inequality 2 here. And I'm going to use pictures because I guess I can, right? So, okay, first of all, there's nothing to be proven if this covering number is infinite. So let's assume it's finite. What does that mean? It means I have K, and K is covered by a finite number of balls of radius epsilon over 2. So now consider a packing. My claim is that any packing can only have at most one point inside one of these balls. So the number of elements in the packing has to be less than the number of elements in the covering. And why is that? So take one of these balls. Right? So let me draw it over here. It has radius epsilon over 2. Of course, the balls don't need to look like round balls in the plane, but the reasoning I'm going to use is completely general, right? Okay. Now assume to get a contradiction that I have my packing Q, right? My epsilon packing Q, and there are 2 points of Q in here. So here I have the center of the ball, right? So that's x sub x prime. I don't know, a point from the epsilon over 2 net. And I can just use the triangle inequality to say, well, the distance from Q to Q prime is at most the distance from Q to X plus the distance from X to Q prime. Each one of these two distances is less than or equal to epsilon over 2. Therefore, the sum is less than or equal to epsilon. But that's a contradiction, right? So if Q and Q prime belong to the same epsilon packing, their distance is greater than epsilon, so you cannot have 2 points of the packing inside the same ball. The consequence of that is that any epsilon packing must have cannot have more points than there are balls in an epsilon over 2 covering. So the largest packing is bounded by the smallest covering of radius epsilon over 2. So this is inequality 2. And now I'm going to prove inequality 1, which is only slightly more complicated. And it's also very geometrical. It's something, it's a nice exercise when you're dealing with metric spaces, but because we need it for this theory of compactness, I'm going to do it now. Okay. So I have now K. And again, I'm going to assume that this guy is finite. If it's infinite, then, well, infinite is greater than either infinite or any number. So I have K here. And I have my packing. So I have these points. The set Q, which is an epsilon packing, of maximum size. So let me call this Q sub 1, Q sub 2, Q sub 3, sub 4, Q sub 5, Q sub K. There may be more points in here. It's of maximum size, meaning it has size P of K epsilon. If it's an epsilon packing of maximum size, I claim that it's also an epsilon net. Therefore, the smallest epsilon net must have size less than or equal to pk epsilon. Okay, why is Q an epsilon net? Take a point, x. I have to show that there's a point of Q within distance epsilon from this x. Now, if x is one of the points Q1, Q2, Qk, one of the points of Q, then there's nothing to be proven, right? So you can take the point to be, right? So if x is equal to Q2, I know that Q2 is within distance epsilon from x. No big deal. So suppose that x does not belong to Q, then you have that Q union x is not an epsilon packing. right? So because Q is an epsilon packing of maximum size, I add a point, it cannot be an epsilon packing. Well, if a set is not an epsilon packing, there must be a pair of points within distance less than or equal to epsilon. Now, the Q's are all within distance larger than or equal to epsilon, right? The Q's form an epsilon packing. So say the distance between Q1 and Q2, Q1 and QK, Q1 and Q3, Q2 and Q3, all of these are larger than epsilon. So the small distance that I have now that I added x must be the distance between x and some other point. So some distance between x and another point must be less than or equal to epsilon. Therefore, given an x that's not in Q, I'm nevertheless able to find a point in Q within distance epsilon from x. Therefore, Q is an epsilon net. And we're done. So we show that if I have an epsilon packing, I also have an epsilon net. Therefore, the size, the largest packing is if I have an epsilon packing of maximum size, that's an epsilon net. So the size of the largest epsilon packing is an upper bound for the size of the smallest epsilon net. So we have these inequalities, and again, the importance of them is that now I know at the very least that if a totally bounded space is a space where all packing numbers are finite. However, there's something else that we're going to use later, which is not entirely obvious given these definitions. Okay, so if K is totally bounded, all the covering numbers are finite, all the packing numbers are finite. If K is not totally bounded, then some covering number is infinite, some packing number is infinite. But I want to prove something else. I want to prove that if a set is not totally bounded, then there is an infinite epsilon packing. Notice that this is different, right? So again, this number is just a supremum over of sizes of epsilon packing. So one way in which this number could be infinite is just saying, okay, this number is infinite because I have a finite epsilon packings of arbitrarily large sizes, right? But now I want to prove that when the set is not totally bounded, then actually you have one single infinite epsilon packing. And that we're going to use later. Basically to relate this concept of total boundedness to compactness as we want to, right? So everything is going to go back to compact metric spaces, this grand equivalence theorem. And we're gonna prove a theorem soon that says that if a space is not totally bounded, then there's a continuous function from this space to R that is unbounded, right? So, okay. But first of all, let's give this geometric characterization of non-totally bounded sets. Proposition. And maybe I should erase some more. If K is not totally bounded, this implies that there exists, S contained in K, infinite epsilon packing for some epsilon. And the proof of this is also very geometrical. I'm just going to give it using a picture. Though in this case it's slightly more complicated because it involves an inductive construction. So hopefully you can read this relatively well. Yeah, this is not so obvious, so it's a bit blurred and it chose the wrong chalk. So this is saying that if a set is not totally bounded, meaning if n k epsilon is infinite for some epsilon, and then there exists an infinite epsilon packing. How do we prove that? So I'm just going to assume that K is not totally bounded. So I'm going to assume that n k epsilon is infinite And for this epsilon, I'm going to find an epsilon packing, an infinite epsilon packing. How do I define this? I'm going to define it inductively, right? So I take K. So K is not totally bounded, so let me make it like large. I take K. I take X1. I want to build a packing, right? So I need a point X sub 2. The next choice has to be a distance larger than epsilon from X1. How do I know that exists? Well, I know that nk epsilon is infinity, right? So there's no epsilon net of size 1. What does it mean? It means that x1 by itself is not an epsilon net. So if I take the ball of radius epsilon around this guy, there must be something outside, right? So if everything was inside this ball, then x1 by itself would be an epsilon net, but we know there's no finite epsilon net just because of this. Okay, and how do I continue? Well, x1, x2 is also not an epsilon net because there's no finite epsilon net. So I take these two balls, and there must exist a third point that lies outside them. And I just keep doing this, right? So suppose I build x sub n. All these distances are larger than epsilon. Now I look at all these balls around x sub 1, x sub 2, up to x sub n. These guys do not form an epsilon net because there's no finite epsilon net. Therefore, there must exist an x sub n minus 1 that lies outside these balls and has distance greater than epsilon with everybody. And you can continue forever, right? So the point is that no finite set of points that you pick can be an epsilon net. So if you pick these guys to be a distance greater than epsilon from one another, you know that at any step you're not going to spawn it. You're not going to stop. There's always going to be some other point that is a distance greater than epsilon for all the finitely many points you've chosen. And now you're done because your infinite epsilon net is just a sequence. Your finite epsilon packing, sorry. Right? So it turns out that when K is not totally bounded, it's not just that there exists finite epsilon packings of arbitrarily large sizes. There actually exists an infinite epsilon packing. Okay. And now we can get to the main theorem of this video, which is a theorem saying that basically, well, we can write it in two forms. I'm going to write it in the form that's sort of the contrapositive. So we know that if a metric space is compact, all continuous functions are bounded, right? This is even true in topological spaces. So I'm now going to prove that if a metric space is compact, if all continuous functions over a metric space are bounded, then this metric space has to be totally bounded. So it means that if I take, right, the whole metric space is just x or k, and this metric space has to be totally bounded in order for continuous functions to be all bounded over it. But as I said, I'm going to prove that in contrapositive form. So what is a contrapositive form? It's I'm going to prove that if I have a metric space that's not completely bounded, not totally bounded, sorry, then there is a continuous function defined over this space, which has supremely equal to infinity. So that's the same thing that we did for completeness, right? We showed that if a metric space is not complete, then there exists a continuous unbounded function from this space to R. Now we're going to prove that if a metric space is not totally bounded, there's a continuous unbounded function from this space to R. And therefore, if a metric space is such that all continuous functions are bounded, it must be complete and totally bounded. So that's one of the steps, one of the implications of that grand equivalence theorem. So, okay, let me write a statement here, and then I'm going to draw pictures, and I'm going to try to convince you that these pictures actually make sense. Theorem. If I have a metric space that's not totally bounded, then there exists an f from x to r continuous with infinite supremum. And in order to prove this, we're going to have to use, or kind of, we have a characterization of what it means to be not totally bounded. So a space is not totally bounded if for some epsilon contains an infinite epsilon packing. So I'm actually going to call it delta packing just because that's a node. Zero. And I can assume without loss that this guy is countable such, right? So sorry, I forgot to say infinite, Sn, and so on and so forth. So let me pretend that X is a real line and just draw a few of these points over here. So here's X sub 1, sorry, S sub 1, S sub 2, S sub 3, and there are many others, right? So I know that it exists in a delta packing for some positive delta. I'm assuming it's countable because it's an infinite set. It can take a countable subset. And I'm going to define R just to simplify things as delta over 4. Okay, why do I do this? I know that these distances are all greater than R. Sorry, are all greater than 4R. And same with the next guy. So now what I'm going to do is this. So I'm going to define a continuous function. I'm going to try to draw its graph over here, or sketch its graph. And this continuous function is going to be like this. So it's only non-zero when you are close to one of the SIs. So if I take here, this has size R. So here this has size R as well. And because the distance between points are so large, these regions are disjoint. And in each one, so the function is 0 outside of these things that look like intervals because I'm drawing the whole space as if it was one-dimensional. And, well, let me try a different color of chalk just to make things a little bit clearer, perhaps. Right, so I have this function which is 0 outside of these. In reality, they're going to be balls of radius r around the SIs. And inside of these SIs, I want to have something that looks like a little tent. Except that the little tent is going to be taller and taller. Right? So it's going to have height 1 here, height 2 here, height 3, and that's 3, and height k around S sub k. So it's going to get taller and taller. So if I have a function like that, it's clearly that it should be unbounded. And if I do everything correctly, it's going to be continuous. Why is it going to be continuous, you may ask? Well, continuity is a local property. So as long as kind of locally the function behaves well, you're done. Okay, so I'm unfortunately going to have to erase the picture. Otherwise, I'll quickly run out of space. But the idea is that I want to build this function. And that's 0 when you're far from all these points. And it takes this tent shape when you're close. And the tents get taller and taller. Okay, how do we do that? So first remark is that for all x, there exists at most one index with a distance from x. I'm just going to drop the subscript here. There exists at most one point in S within distance r from x. Or sorry, 2r. Within distance 2r. And why is that? Because if there were 2 points, right, suppose that, say, S1 and S2 are within distance 2r from x. That means by the triangle inequality that S1 and S2 are a distance 4r from each other. However, we know that the distance between these guys is strictly larger than delta, and delta is 4r. So the distance between S1 and S2 has to be greater than 4r. So it cannot be that both S1 and S2 are within distance 2r from x. Okay, so there's a remark that's going to be very useful. It basically means that these tents I'm going to draw are very well spread. So let me define for each j in n, I'm going to define a function f sub j of x that's going to be continuous, and it's going to take the tent shape that I described. If you might have to think a little bit, well, how do you get the tent shape to work? I'm just going to take something like this. Well, it's j times the maximum of 0 and r minus the, so maybe I'm going to move this, sorry. Okay, so it's, yeah, f sub j of x is equal to j times the maximum of 0 and r minus distance from x to x sub j. This is defined for any j, right? So and this is continuous. Okay, look, what is this doing, right? So what is this function like? This is one of the tents, right? So let me draw here f sub j. I have s sub j. So this function, what is its value at s sub j? Well, this is 0, this is r, this is j. So this is j times r. And then decreases linearly with distance until you're at distance r. When you reach distance r, well, we have r minus r, which is 0. And this gives you a 0 for all distances greater than r. So the graph's like this, a little tent. It's actually a narrower tent that I drew before, because the width of the tent is just r in any direction, or 2r if you want. Before I had tents of width 4r. And now I'm going to define my f. So notice that this function here is continuous, defined over the whole space x, and it's continuous. Well, distance to a fixed point is continuous, it's Lipschitz. R minus that is also continuous. Maximum of 0 and something continuous is continuous, that you can check. And multiplying by a constant j makes it continuous. And now I'm going to say that f of x is equal to fj of x if distance from x to x sub j is less than or equal to 2r and is 0 otherwise. So this is how to find the function f. Why is this well defined? Well, because I know that for each x there's at most one index j, which is just j of x, such that the distance from x to x sub j is less than 2r. So for each x, I know how to say, well, either it's close to one specific f sub j, and then f of x is f sub j of x by definition, or it's far from one f sub j's, and then the function takes value 0. This function is unbounded, and that we can prove just by looking at the tents, right? So notice that for all j and n, we have that f of s sub j is what? It's, well, if I compute f of s sub j, right? So I'm in this case, I'm just saying, okay, take x equal to s sub j. Then I'm computing fj of s sub j, and that we know is j times r. So these values are unbounded because r is positive, right? R is delta over 4. When j goes to infinity, this goes to infinity. Oh, great. F is an unbounded function. How do I know that it's continuous? And that's our last challenge in the proof. We have to prove that this guy is continuous. Okay, so now I have to erase some things. But hopefully the proof is going to be clear. And I mean, perhaps the simplest way to prove that this function is continuous, okay, we're going to use the fact that f coincides with f sub j when you're close to s sub j, right? So what is this function like? Take a point x in my space x. So I'm going to consider two possibilities, okay? One is that d of x s sub j is greater, and I'm just going to use some arbitrary threshold here between r and 2r. Okay, what is this? So suppose that distance from x to x sub j is greater than 3r over 2 for all j. So what does that mean? Well, take some s sub j, and I know that f coincides with that f sub j in the neighborhood, right? So if I take this kind of distance r here and r here, I have my little tent, perhaps a very tall tent, but it's a tent nonetheless. And outside I have 0. And maybe I have tents around other points s sub j prime. But one defining thing is that when this is true, then I have that f is equal to 0 in a neighborhood of x, right? I want to prove continuity at the point x. And I'm claiming that when this is true, then f is 0 in the neighborhood of x. Why? Because I'm saying that if I take a ball with, say, radius r over 2 around this guy, there's no point s sub j that is inside this ball. So the function is constant equal to 0. And a function that's constant equal to 0 in a neighborhood of x has to be continuous at x, right? Take a sequence that converges to x sub n, eventually enters this ball and never leaves, and then f of xn is equal to 0 for all n large enough, which means that f of xn converges to 0, which means that f of xn converges to f of x, because in this case, f of x is 0. So great. So this is one case. Again, what I want to do is to prove that a function f that I defined before, by pasting together the little tents, that's continuous. So I've proven that it's continuous at any point x that's at large distance for all s sub j's. So now I want to consider the case of a smaller distance. What does that look like? Well, okay, I have a little tent around s sub j. I have x. X might be in here, might be a little bit farther away. So this is like 3r over 2. And my claim is that in this case, there is a j in n that satisfies this. So in this case, f equals f sub j in the neighborhood of x. Why? First of all, notice that the fact that the distance from x to x sub j is less than or equal to 3r over 2 means that this j is precisely this value j of x, right? The unique value of j such that x is close to x sub j, s sub j. Now, actually, this works in the neighborhood of x. In the neighborhood of x, all points are at distance less than 2r from this specific set f sub j. And now watch. So, because basically, okay, in this case, I have that this guy, f is equal to f sub j over an open ball around x of radius r over 2, because this open ball is contained in the open ball of radius radius 2r around s sub j. And the way we defined f is such that over this open ball around s sub j, the closed ball rather, over this closed ball around s sub j, then f is equal to f sub j. And why is that good? Again, right? So now I want to prove, this is case 2, sorry. I want to prove that f is continuous at x. And I'm assuming this case, which means that f is equal to f sub j inside this ball. So take a sequence x sub n converging to x, then f of x sub n is equal to fj's x sub n for n large. And why is that? Because for n large, I know that x sub n has to be in this ball. And now watch. Well, now you just notice that by continuity of f sub j, which we know, this converges to f sub j of x, which is f of x. Right? So in this case, I'm using the fact that in this case, f of x is equal to f sub j of x. It's actually true not only at x, but in the neighborhood of x. And since fj is continuous, then f is continuous. Okay, let's recap this real quick, okay? First of all, I started from a not totally bounded space, and we know that in a not totally bounded, I have an infinite delta packing for some delta greater than 0. What is that? Is a set of points in x that are all within distance greater than delta from one another. Now, given these points, I defined these 10 functions which are taller and taller around these points, but really using just a narrow region around this point of radius r, right? So I take these 10s so that they're equal to 0 if your distance greater than r from f sub j. And now I define a function f that agrees with each f sub j in a region of radius 2r around s sub j. And I had to notice that these regions do not overlap, that for each x, there is at most one index j such that the distance from x to s sub j is less than or equal to 2r. So it means I have these bunch of non-overlapping regions, so f is equal to f sub j in these regions, in each one of these regions, and f is 0 outside. And now I want to prove that this function f that I built is continuous. What do I know? I know that these f sub j's are continuous, and I know that the 0 function is constantly continuous as well. So how do I prove that it's continuous? Basically, what I'm using is the following fact. Suppose I have a function f, and for each point in the domain, there's a little neighborhood of this point, a little ball around this point, where f coincides with a continuous function. Then f has to be continuous over the entire domain. And how do we use this? Well, basically, we showed that points in the domain x come in two kinds, right? Either the distance from x to s sub j is larger than 3r over 2 for all j, in which case I know that the function is 0 in a neighborhood of x, or I have the situation where the distance from x to s sub j is less or equal to the 3r over 2 for some j, and therefore this j is unique, and f coincides with f sub j in a neighborhood of x, right? So all points of this ball were contained in here, and here the function f and the function f sub j coincide, and so I can borrow, so to speak, the continuity of f sub j to prove the continuity of f. And this means I'm done because remember, the way I built this function with the higher and higher, the taller and taller tents, right, all over sitting on top of each s sub j, means that the function in the end is going to be unbounded. If I compute f of s sub j, that's always equal to j times r. J times r goes to infinity when j goes to infinity. Therefore, we've built a continuous unbounded function from a delta packing. Which means that if you have an infinite delta packing, there will be a continuous function that's unbounded defined over your space. In particular, if a space is not totally bounded, it cannot be compact. Well, of course, we want to prove the converse of that, but that comes later. So I'm done by now. Thank you.